continue with our discussion on quantum states of electromagnetic field. We started to discuss coherent states in the last lecture toward the end. Do you have any questions from the last lecture? Okay, so let's continue with our discussion on coherent states. So let me recall, we are looking at single mode states. That means states in which the electromagnetic field corresponding to one mode is excited. And this particular coherent state is a state which is defined as the eigenstate of the annihilation operator A. Now, because A is not a Hermitian operator, alpha can be complex. The eigenvalues alpha can be complex. So this equation implies alpha A dagger is equal to alpha star Now, in the last class, we wrote this alpha as a superposition of the nth states, because the nth states form a complete set of functions, complete set of states. You can expand any state in terms of these nth states, and Cn are the expansion coefficients. We had calculated the values of Cn in the last class, and we had shown that this is exponential minus mod alpha square by 2 sigma alpha raised per n by square root of n factorial get n. And alpha satisfies, of course, the normalization condition alpha is equal to 1. Okay, so this is a state which is a superposition of the various nth states. An nth state is a state which is an eigenstate of the Hamiltonian operator. If you measure the energy of a nth state, you will always precisely get the same value every time. This is a superposition of nth states, and so let me try to calculate what is the probability of observing n photons in this state. So Pn is equal to mod n alpha, and if you use this expression for alpha, you can show that this is minus mod alpha square raised per n by n factorial. Now I can relate alpha to the expectation value of the number of photons. So let me calculate the expectation value of n operator. This is alpha A dagger A alpha. A alpha is alpha A dagger is alpha star alpha, and because alpha is normalized, so this is mod alpha, and this is the expectation value, which I just write as the average number of photons n bar. So the probability of observing n photons is exponential minus n bar raised per n by n factorial. This is the Poisson distribution. So the probability of observing n photons is given by this equation. So for example, the probability of observing 0 photons is exponential minus n bar, n is equal to 0. The probability of observing 10 photons is exponential minus n bar raised per 10 by 10 factorial. So this is in a state of superposition of the nth states, and what we have calculated is the probability of observing a certain number of photons in that state. Now let me calculate what is the variance in the number of photons in the state. So remember, variance is given by n square expectation value minus n expectation value whole square. So for this I need to calculate n square expectation value. So n square expectation value alpha a dagger a alpha. Now I have this relation a dagger is equal to 1. So this implies a dagger minus a dagger a is equal to 1. So I replace this a dagger by 1 plus a dagger a, and I get n square expectation value is alpha a dagger into a dagger a plus 1 into a alpha. So this is equal to alpha a dagger square a square alpha plus alpha a dagger a alpha. A operating twice on alpha gives me alpha square. A dagger operating twice on alpha bra gets me alpha star square. So this is mod alpha raised per 4 plus this is mod alpha square. So that's expectation value of n square. Expectation value of n is mod alpha square. So I can substitute these two expressions in this equation to find out what is the variance in the number of photons in this coherent state, and that comes out to be, so delta n square is equal to mod alpha 4 plus mod alpha square minus mod alpha 4, which is equal to mod alpha square, which is equal to n bar. So the variance in the number of photons in the state is equal to the average number of photons in that state. So the uncertainty in the number of photons is square root of n bar. So this means that the fractional uncertainty in the number of photons is given by 1 by square root of n bar. So if you have an electromagnetic field generated in a single mode coherent state, the fractional uncertainty in the number of photons in that state decreases as n bar increases. That means as alpha increases, as mod alpha increases, the fractional uncertainty in the number of photons in that state decreases and is given by, decreases as 1 by square root of n bar. And this is a characteristic feature of a Poisson distribution. Now, to relate this coherent state to a classical electromagnetic field, let us try to calculate what is the expectation value of the electric field in this state. So recall, the electric field operator is given by I times square root of h cross by h cross omega by 2 epsilon 0 v into a exponential minus I omega t minus kz minus a dagger exponential I omega t minus kz. We are assuming this mode, the coherent state, to be in a mode which is propagating along the z direction and is linearly polarized. So I'm not writing any vector here. It's a scalar electric field. Now let me define two quantities, E naught, which is 2 h cross omega by epsilon 0 v, and chi, which is omega t minus kz. So in terms of these two expressions, the electric field operator becomes I times E naught by 2 a exponential minus I chi minus a dagger exponential I chi. Please note that this electric field is a time dependent operator. We are using the Heisenberg picture in which the electric field operator is a time dependent operator and the state is time independent and given by this expression for this. You can do the same calculations in the Schrodinger picture and all expectations values that we are calculating will exactly have the same values in the Schrodinger picture. So this is the electric field operator. Chi contains time and z dependence here, and so let me calculate what is the expectation value of the electric field in the coherent state? So expectation value of E is equal to alpha E alpha, which is equal to I E naught by 2 alpha A alpha exponential minus I chi minus alpha A dagger alpha exponential I chi, which is equal to I E naught by 2. What is this? This is alpha into alpha alpha, which is 1, minus I chi minus alpha A dagger is alpha star alpha. So this is alpha star exponential I chi. So alpha is complex. So let me write alpha is equal to mod alpha exponential I theta. So expectation value of E becomes I E naught by 2 mod alpha e to the power minus I minus theta minus mod alpha e to the power I minus theta, which is equal to I E naught by 2 mod alpha, and this remaining factor within this bracket is minus 2I sine I minus theta. So this 2 cancels off, I into minus I is 1, so E naught mod alpha sine omega t minus kz minus. So notice that the expectation value of the electric field varies as sine omega t minus kz minus theta, exactly like a classical electromagnetic field. The amplitude of this is given by E naught times mod alpha. If you recall, when we looked at the nth state, the electric field expectation value in the nth state was equal to 0. So the nth state is an eigenstate of the Hamiltonian operator. It has a fixed number of photons, exactly a well-defined number of photons, and the expectation value of the electric field was 0 there. That is not a representation of the classical electromagnetic field. This state alpha, which we are looking at, the coherent state, which is an eigenstate of the annihilation operator A, if you prepare a state in this, if you prepare an electromagnetic field in this state, expectation value of the electric field in this state is E naught mod alpha sine omega t minus kz minus theta, and varies in exactly the same fashion as a classical electromagnetic field. Of course, this is a quantum field, it's not a classical field, because as you can see now, as you will see, the electric field has uncertainties. This is the expectation value of the electric field. To find out what is the uncertainty in the electric field, we need to calculate expectation value of E square. So for example, let me calculate the expectation value of E square. So this is alpha E square alpha. So what is E square? Now E, remember, we had written as E was written in terms of A and A dagger like this. So E square is minus E naught square by 4 A exponential minus I chi minus A dagger exponential I chi into A exponential minus I chi minus A dagger exponential I chi, which is equal to minus E naught square by 4 A square exponential minus 2 I chi minus A dagger minus A dagger A plus A dagger square exponential 2 I chi. So expectation value of E square is minus E naught square by 4 alpha A square alpha exponential minus 2 I chi let me bring it in the front. So plus alpha a dagger square alpha exponential 2 I chi minus alpha a dagger alpha minus alpha a dagger a alpha. So this is equal to minus E naught square by 4. So this is nothing but alpha square. So alpha square exponential minus 2 I chi. This is alpha star square exponential 2 I chi. Now please note that a dagger on alpha is not alpha star alpha. A dagger operates on bra alpha. So I need to replace a dagger in terms of a dagger a by using the commutation relation. So a dagger is a dagger a plus 1. So I get minus alpha a dagger a alpha, which is mod alpha square, and then minus 1 minus mod alpha square. So this a dagger a expectation value is mod alpha square, a dagger expectation value is mod alpha square plus 1, and so expectation value of E square becomes expectation value of E square minus E naught square by 4. Okay, so this is mod alpha square exponential minus 2 chi minus theta, because alpha square is mod alpha square exponential 2 theta. So I take it here plus mod alpha square exponential 2 chi minus theta minus 2 mod alpha square minus 1, which is equal to minus E naught square by 4. So this is mod alpha square into sum of those two exponential is 2 cosine of 2 chi minus theta minus 2 mod alpha square minus 1. Let me take the minus sign inside. So I get E naught square by 4 2 mod alpha square into 1 plus cos 2 chi minus theta plus 1. That's the minus sign here. Okay. So this, I take the minus sign inside. So this becomes 2 mod alpha square plus 1. And then I have minus 2 mod alpha square cos 2 chi minus theta. So what is this value? Cos 2 theta is 1 minus 2 sine square theta. So I can replace this and I get expectation value of E square is equal to E naught square by 4 into 1 plus 4 mod alpha square sine square chi minus theta. Okay, and remember that expectation value of E we had obtained earlier was equal to E naught mod alpha sine chi minus theta. So the variance in the electric field is equal to expectation value of E square minus expectation value of E whole square, which is equal to so expectation value of E square is this. So the second term is E naught square mod alpha square sine square chi minus theta. That cancels with this, and I get E naught square by 4. And E naught square if I replace, so this is 1 by 4 2 h cross omega by epsilon 0 v. So this is h cross omega so delta E, the uncertainty in the electric field, is square root of h cross omega by 2 epsilon 0. Independent of mod alpha. Independent of mod alpha, independent of time, and it's a constant. The expectation value of the electric field increases as mod alpha increases. The uncertainty in the electric field remains constant. So, I can actually picturize the electric field variation in this form. So, the electric field expectation value. So, let me draw a curve representing the expectation value of the electric field first. So, this is E naught mod alpha sine omega t minus kz minus theta. So, let me plot at z is equal to 0. Okay. So, this will go as E naught mod alpha sine omega t minus theta. So, it will have some variation like this. So, let me plot for example with theta equals 0. So, it goes like this. This is the expectation value going like this. There is an uncertainty of square root of h cross omega by 2 epsilon 0 v of the electric field at every instant of time. So, let me plot the upper bound and the lower bound here and the lower region. So, this will represent, so this is uncertainty in the electric field at any time. This remains constant, independent of time. And so, this is a representation of the coherent state. Remember, this uncertainty is independent of mod alpha. So, if you take a coherent state with a large value of mod alpha, this expectation, this height is quite large, amplitude is quite large, because amplitude is E naught mod alpha, and the uncertainty is always square root of h cross omega by 2 epsilon 0 b. So, this field resembles more and more of a classical field, and for very large values of mod alpha, this noise that is present in the electric field becomes negligibly small compared to the amplitude itself, and the field tends more and more towards a classical field. It's always noisy, there's always noise in the electric field. Please remember of this amount in this coherent state. And this state, this noise is actually the same noise that you will find in a state which is the vacuum state. Because a vacuum state, if you go back and look at this equation for the definition of the coherent state, a vacuum state corresponds to A alpha is A0 is equal to 0. So, vacuum state corresponds to alpha is equal to 0, and so the expectation value of the electric field in the vacuum state becomes 0 because mod alpha is 0, but there is uncertainty in the electric field which is the vacuum fluctuation. So, this noise that is present in a coherent state is exactly the same amount of noise that is present in the vacuum state. As the amplitude of the coherent state increases, the fractional uncertainty in the electric field decreases because delta E remains constant while the amplitude keeps on increasing, and finally you get closer and closer to the classical state of electromagnetic field. So, in this state, expectation value of electric field is E naught mod alpha sine omega t, and since I am assuming theta is equal to 0 and delta E is equal to square root of h cross omega by 2 epsilon 0. Okay. Now, there is another pictorial representation that is used to represent the states which we had discussed earlier, and that is in terms of the uncertainties and the expectation values of the quadrature operator x and y. Please remember, we have defined a quadrature operator as x as a plus a dagger by 2 and another quadrature operator y by a minus a dagger by 2i. So, let us calculate what is the expectation value and what are the uncertainties in the two quadrature operators when the field is in a coherent state. Okay. So, expectation value of x is equal to alpha a plus a dagger by 2 alpha which is equal to half of alpha plus alpha star, which is equal to half of mod alpha e to the power I theta plus mod alpha e to the power minus I theta, which is equal to mod alpha cos theta. Okay, so that's the expectation value of x. What is the expectation value of x square? We need to calculate the variance or the uncertainty in x. So for that I need to calculate expectation value of x square, which is equal to alpha a plus a dagger whole square by 4 alpha, which is 1 by 4 alpha a square plus a dagger square plus a dagger plus a dagger a alpha, which is equal to 1 by 4. Now I can replace a dagger by a dagger a plus 1. So I get alpha a dagger square, sorry, a square plus a dagger square plus 2 a dagger a plus 1 mod alpha, which is equal to 1 by 4. A square expectation value is alpha square, a dagger square expectation value is alpha star square, a dagger a expectation value is mod alpha square plus 1, which is equal to 1 by 4 mod alpha square e to the power 2I theta plus mod alpha square e to the power minus 2I theta plus 2 mod alpha square plus 1. This is equal to 1 by 4 mod alpha square into 2 cosine 2 theta plus 2 mod alpha square plus 1. So this is 2 mod alpha square into 1 plus cos 2 theta, which can be written as cos theta in terms of cos theta. So you get 2 mod alpha square into 1 plus cos 2 theta plus 1. So cos 2 theta is 2 cos square theta minus 1. So this becomes expectation value of x square becomes 1 by 4 2 mod alpha square into 2 cos square theta plus 1, which is equal to mod alpha square cos square theta plus 1 by 4. That is the expectation value of x square. So the variance in x operator is equal to x square average minus x average square. X average we have just now calculated is mod alpha cos theta. So this becomes 1 by 4. So the uncertainty in the x quadrature is half, again independent of the magnitude of alpha. I can similarly calculate the expectation value of y and the expectation value of y square, and from these two I can calculate delta y, and the expression I leave it to you to calculate, this comes out to be again 1 by 2. Delta y is also 1 by 2, delta x is also 1 by 2. Please remember, x and y satisfy a commutation relation which we have discussed earlier. X comma y is equal to I by 2. Now when you have a commutation relation between two operators, they would have to satisfy an uncertainty relationship between them. In fact, if you have two operators satisfying this relation, AB is equal to IC, then you can show that delta A into delta B, the product of the uncertainties is greater than or equal to half of mod of expectation value of C. If you have two operators A and B satisfying the commutation relation AB is equal to IC, then delta A times delta B must be greater than or equal to half of the modulus of the expectation value of C. So, because x and y satisfy this equation, delta x times delta y, because C is just 1 by 2, this must be greater than or equal to 1 by 4. So, the product of the uncertainties in the x quadrature and the y quadrature must be greater than or equal to 1 by 4. For the coherent state we have just now calculated, delta x is half and delta y is half. So, for the coherent state, delta x delta y is equal to 1 by 4, and this is called a minimum uncertainty state. This satisfies the minimum value of the product of the uncertainties in x and y, and hence it is called the minimum uncertainty state. This is the smallest value of the product of the uncertainties in x and y. You may have states for which this product is greater than 1 by 4. They will not be minimum uncertainty states, but these states are special states for which the product of the uncertainties in x and y is actually 1 by 4. And coherent state, which we are discussing, is one of the minimum uncertainty states. So, what we have got is the following. We calculated the expectation value of x. So, what you got is expectation value of x is equal to mod alpha cos theta. I left it as a problem to you to calculate the expectation value of y operator. You can show that this is mod alpha sin theta. We have also seen that delta x is equal to half and delta y is equal to half. So, using these quantities, I can draw the phasor diagram corresponding to a coherent state. This is x, this is y. So, I put a point corresponding to the expectation value of x and y. So, this angle, if I join this line, this angle is theta, expectation value, so, and this distance is mod alpha. So, the expectation value of x is mod alpha cos theta, expectation value of y is mod alpha sin theta, and there is an uncertainty around this point, and this radius is half. So, a coherent state is represented in the phasor diagram by a small circle of radius half. The center of the circle is situated at a distance mod alpha from the origin, and this line, the radial line, makes an angle theta with the x axis. So that the expectation value of x is mod alpha cos theta, the expectation value of y is mod alpha sin theta. So, if you look at a state which happens to be the vacuum state, please note that in the coherent state we have this equation, and a vacuum state is defined by, so vacuum state corresponds to alpha is equal to 0. So, the same phase, so I can actually use this expression that we have got to obtain the parameters of vacuum state, and I get for a vacuum state x average is equal to 0, y average is equal to 0, delta x is equal to half, and delta y is equal to half. So in the phasor diagram, vacuum state will be represented by a circle of radius half, and on the origin, because expectation value of x and y are 0, and there is uncertainty of half in both x and y quadratures. So for a coherent state, this is mod alpha, and remember mod alpha is related to the average number of photons. The average number of photons is equal to mod alpha square. So this distance square is expectation value of the number of photons in that state, which is n bar, and so if you increase the value of alpha in a coherent state, this distance will increase, of course, and the radius of the circle remains constant because that is independent of mod alpha. And if you look at a vacuum state, this corresponds to a state in which the expectation values of x and y are 0, and the noise, the uncertainty in x and y is still half. So coherent states are states which are closest to the classical electromagnetic field, because as you have seen here, the expectation value of the electric field in this state, in the coherent state, varies as exactly like in a classical electromagnetic field. Expectation value of electric field goes as E naught mod alpha sine omega t minus kz minus theta. And a laser, which is a very well stabilized laser, the light coming out of that kind of a laser is a coherent state. It doesn't have a precise number of photons. There is an uncertainty in the number of photons. There is an expectation value you can calculate. You can calculate the variance in the number of photons. You can calculate the expectation value of the electric field, the variance in the electric field, and all this you can calculate for the coherent state, and this is a state which is closest to a classical electromagnetic field. So, do you have any questions in the discussion that we have had in coherent states? Please note that we are still discussing single mode states of electromagnetic field, in which the excitation is only in one of the modes of the electromagnetic wave. We will consider another kind of states later on, squeeze states, before we move on to multimode states. So in this state, in the coherent state, the uncertainty in the x and y quadratures are equal and equal to the minimum values. There can be states in which this product is still the product of delta x delta y, which has the minimum value is 1 by 4. The product is still 1 by 4, but delta x or delta y, one of them could be less than half at the expense of the other one being more than half. So you can have reduced uncertainties in one quadrature at the expense of increased uncertainties in another quadrature, which leads to states which are called squeeze states, which are very interesting, and they are completely non-classical states, and they are finding a lot of applications. So that's the discussion on coherent states. So we will, from next class, we will look at squeeze states and continue with states of single modes of electromagnetic field before we move on to multimode states. Thank you very much.